Hello, eco-conscious viewers, and welcome to another edition of Planet Earth, Our Loving Home. Antarctica's landmass extends for more than 14 million square kilometers, 98% of which is covered by the Antarctic ice sheet. The continent accounts for 90% of the world's ice and 72% of its freshwater reserves. However, climate change is rapidly thawing this ice, and if the entire sheet were to melt, Earth's sea level would rise 60 to 70 meters, an unimaginable outcome for all beings on the planet. Recently, the world's attention has been drawn to the rapidly collapsing Wilkins Ice Shelf, a 14,000 square kilometer mass of floating ice in the western part of the Antarctic Peninsula. A thin 40-kilometer ice bridge, the last piece keeping the shelf in place, shattered in April 2009, an event that is expected to cause the shelf to disintegrate at an even faster rate. To learn more about the effects of global warming on Antarctica, we spoke with Dr. Ted Scambos, lead scientist at the University of Colorado's National Snow and Ice Data Center in the U.S. Dr. Scambos' research covers glaciology, remote sensing, geochemistry, and planetary science. His current studies involve Antarctica's ice sheet, ice shelves, and sea ice. He has briefed former U.S. Vice President and Nobel Peace Prize laureate Al Gore on ice sheets and contributed to the United Nations Intergovernmental Panel on Climate Change report, Climate Change 2007, The Physical Science Basis. Dr. Scambos first discusses the collapse of the Wilkins Ice Shelf.
The Formosat satellite showed us in detail the process that's going on. But there are not large glaciers that flow into the Wilkins ice shelf. So the loss of this ice shelf won't lead to sea level rise by itself. The issue is that other ice shelves in Antarctica are also experiencing a warming trend, particularly in the Antarctic Peninsula and along the north coast of Antarctica. And if they go through the same process, there's no reason to think that they would not go through the same process, then these ice shelves act as a braking mechanism, a means of slowing down the flow of ice off of the continent. Because this ice flow would be more rapid without the presence of the ice shelf, you'll see a rise in sea level as ice comes off of the Antarctic continent and goes into the ocean. So what we think is that in the Wilkins ice shelf, it looks as though there's a layer of salt water that seeps in from the edge and fills a narrow layer just at the waterline level of the ice shelf. And so it means that the Wilkins ice shelf was unstable already from this salt water that has seeped in from the sides. Most ice shelves don't have that. Most ice shelves flow outward into the ocean faster than the ocean water is seeping into this layer. And so most ice shelves are just snow and ice, and when surface water is present, that makes them unstable. But the Wilkins was apparently already unstable because of this brine layer.
The average temperature on the Antarctic Peninsula has increased 2.5 degrees Celsius over a 50-year period, which is about 3.5 times faster than the rest of the world.
I think the warming trend that we've seen in the past 50 years in this area led to a summer where the combination of brine and surface water led to this runaway breakup event. So we saw this in May of last year, and even in July of last year there was further breakup. It looks as though warmer ocean water contributed to this one. These blocks, although it looks like they're breaking away in an event last year, in fact those blocks were already mostly broken and separated from the Wilkins over a decade ago. What happened in this event was that warmer water came in between these blocks and melted the thin layer of snow and ice in between them and allowed them to sort of drift off into the ocean a bit. This left this bridge of ice right here, which was talked about quite a bit this spring. This last little bridge was acting as kind of a brace. Here's the remaining Wilkins ice shelf here. These are all these broken blocks that I mentioned before in the image. This is the area that was lost last year in the disintegration event. And then in early April, we saw another disintegration event, very much like the one that happened a little bit more than a year ago, with the same kind of pattern. We don't have a formosat image of this area, but it appears from the MODIS data, which is what we're showing here, that the breakup was very similar in this ice bridge. And now all of these blocks are likely to sweep out into the ocean, and the Wilkins will lose this whole section in here.
When we return, Dr. Scambos will discuss Antarctica's future with respect to the collapse of other ice shelves. Please stay tuned to Supreme Master Television. Welcome back to Planet Earth, Our Loving Home, featuring the impact of climate change on Antarctica. Dr. Ted Scambos, lead scientist at the National Snow and Ice Data Center at the University of Colorado, USA, is discussing Antarctic ice shelf disintegration due to global warming. In 2002, the Larsen B ice shelf, which had a surface area of 3,250 square kilometers, collapsed on the Antarctic Peninsula's east coast.
In the case of the Larsen B, it looks as though that ice shelf was stable for perhaps 10,000 years prior to the breakup that occurred. So what we're going to take a look here at is large glaciers. What happens to them after the ice shelf is lost? The Larsen B ice shelf used to be filling this entire image in here. These are about 1,500 meter high mountains in the background with these glaciers flowing in between them. And with the ice shelf in place, this glacier was braced by the presence of this thick plate of floating ice, which was then touching various islands and peninsulas, sort of providing a slowing mechanism for the glacier. But what happened after the loss of the ice shelf was that all of the glaciers, this is another satellite image, and this area here is covered with sea ice, just a very thin layer of ice on the ocean surface. This is what's left of the Larsen ice plate. This whole area in here disintegrated in 2002. We made measurements of how fast the glaciers flowed before this ice shelf left and after this ice shelf had disintegrated. We also made measurements before and after in these two glaciers here. And what we saw was that the glaciers that are in the area where the ice shelf disintegrated accelerated significantly after the loss of the ice shelf. That's this period of time right in here. That's when the ice shelf disintegrated. But this glacier here, which is down here south of the area where the ice shelf remained, showed no change whatsoever. So it was proof that the loss of the ice shelf in this area is directly responsible for the speed up of the glaciers and the loss of ice up here on the continent flowing into the ocean.
Dr. Scambos next puts into perspective the rate of ice loss after the collapse of Larsen B.
Here we're looking at elevation maps of the area, and we were able to track the elevation loss in Crane Glacier. So in the years since 2002, this is now February of 2006, there's been a net loss of ice. The ice in the glacier has thinned as it's flowed out more rapidly and drained ice from the continent. So it's now moving at 4 and 5 times as fast as it had been moving before, and the glacier's losing mass. That means that that ice is going into the ocean, and all of this ice in the backdrop right here is also becoming entrained in this glacier and heading out towards the ocean, which means that sea level will begin to rise. Crane Glacier is not particularly large. If it was in your backyard, you would say it was quite large. But by the standards of Antarctica, it's not very large. Certainly by the standards of sea level rise, it's not very large. But it's, again, an example of what will happen elsewhere in Antarctica if this warming trend that's in the peninsula were to extend to other parts of the ice sheet. Now here's a map. All of these red dots in here are places where we were able to measure the flow speed, and we have these blue lines which are contour lines of how fast the ice is flowing. It's now picked up speed tremendously. So here is July of 2002. This is just after the breakup event. The flow speed at this point is about 550, this is 450 here, 550 meters per year is the flow speed at this time. Prior to the breakup, the speed was about 200 meters per year in this upper part of the Crane Glacier right here. So we took measurements of ice flow in this area right here. We also have a satellite that measures elevation repeatedly along this green line. What we see is that the elevation drops through time. This is 2002, 3, 4, 5, 6, 7, 8, 9. The elevation drops suddenly through this part, and the speed up comes back a little bit because of an interaction with bedrock features. As the ice continues to thin, it floats over the top of the bedrock feature that was slowing it down before, and accelerates very rapidly and thins very rapidly, so that now the speed is just under 1,450 meters per year, about 7 times as fast as it was flowing back before the breakup event occurred. So we see a little bit of interaction with bedrock, and then a sudden acceleration as the glacier thins and it flows more easily through the fjord and out into the ocean after the loss of the ice shelf.
We are appreciative for Dr. Scambos' insightful research into the state of Antarctica. May we all live sustainable lives to halt climate change and end the thawing of this important continent. This concludes part 1 of a closer look at the melting of the Antarctic with Dr. Ted Scambos. Please join us next Wednesday on Planet Earth, Our Loving Home, for part 2 of the interview. Thank you for viewing today's edition of our program. Up next is enlightening entertainment following noteworthy news. May your life be filled with heaven's boundless love.
For more details, please visit www.suprememastertv.com/PE.